Hello everyone, I'm Jialei Wang from Tsinghua University. Today, I'll present our work BET, Black Box Efficient Testing for Convolutional Neural Networks. With the rapid development of artificial intelligence, CNNs have been widely deployed in real world, such as face recognition, autonomous driving, and speech recognition. However, recent studies reveal that CNNs are not safe enough. CNNs may have unexpected or incorrect prediction behaviors due to biased training data, overfitting, and so on. For example, given an original image panda, the adversary can add some perturbations to the image, making CNNs misclassify this image to the gibbon. In our work, we aim to test CNNs and identify defects of them before they are deployed. We survey related works in this topic and find various testing methods have been proposed. Existing testing methods can be categorized into white box testing methods and black box testing methods. For white box testing methods, although they can effectively identify defects for CNNs, they often require fore-inner knowledge of target models, such as model structures and model parameters. This is impractical in scenarios where model inner knowledge is inaccessible. Thus, we mainly focus on black box testing methods. However, existing black box testing methods are not efficient enough. They need to frequently create target CNN models. In this work, we aim to propose a new black box efficient testing method, BET. The overall workflow of BET is shown here. BET initializes the current best test case with the given original input. Then, BET iteratively searches erroneous inputs based on the best test case. Particularly, in each iteration, BET generates continuous perturbations and adds them to the current best test case to get the modified test case. Then, the modified one is sent to query targeted models to check whether an erroneous input is acquired. The whole process iterates until the query budget is exhausted. More details are given as follows. We first introduce the tunable object function. Our tunable object function guides the testing process to explore different decision boundaries and thoroughly test CNNs. If the objective function targets a specific label, the testing process will be led to enter the decision boundary of this specific label and generate erroneous inputs with the corresponding label. Besides, the objective function is tunable, making BET could explore different decision boundaries and perform through testing. We propose tunable object functions for differential testing and single model testing. For differential testing, we help you find erroneous inputs which trigger behavior inconsistencies among multiple models. These models have similar functionality. For example, given two CNN models C1 and C2 with similar functionality, an erroneous input is found if C1 prediction is different with C2 prediction. We propose the DOF to identify inputs that can maximize the prediction difference between the target model with other models. In DOF, the first item means fully exploring the target model C, where Li is dynamically adjusted for exploring different decision boundaries of the model. The second term aims to find disagreements between the target model C with a batch of other models, as such disagreements indicate erroneous inputs are found. For single model testing, we focus on one target model C to find erroneous inputs. We propose the SOF to fully test the target model C, where Li is dynamically adjusted for exploring different extreme boundaries of the model. We then introduced how to generate continuous perturbations. Let's see a basic testing process. A tester generates many test cases to formally test the CNN model. Here, how to generate test cases is the most important problem in a testing process. The essence of generating test cases is to add perturbations to the images. So, how to elaborately craft perturbations is the crux of existing work. However, existing blackboard methods generate random noise as perturbations, which restricts their efficiency in finding audience inputs. In this work, we aim to analyze the weakness of CNNs and utilize the weakness to generate special perturbations that effectively reveal model defects. We first analyze the workflow of CNN and aim to find the weakness of CNNs. The core function of CNNs is the convolution operation, which is a linear operation that involves the multiplication of a set of weights with input. In this slide, we can see that perturbations is multiplied by the kernel, and the result of the multiplication is out. We hope to maximize out. In detail, out represents changes that will propagate to inner layers behind the current convolution layer. In general, the bigger the out, the more likely to acquire audience inputs. We use the image on the right for an intuitive exploration. An audience input needs to cross the decision boundaries of its original prediction. The larger the out, the easier it is to get the audience inputs. Thus, we aim to maximize out. So, the question left is how to maximize out. To solve this problem, we first simplify this problem. Given a simplified kernel, positive 1 and negative 1 represent different kernel weights. If we generate perturbations whose size are different from the size of kernel weights, the operation result out is 0. In contrast, if we generate perturbations whose size are the same as the size of kernel weights, the operation result out is 4. Inspired by this, to maximize out, perturbations should have the same size as the kernel. We further consider a more complex kernel, which have more elements as we have shown in Figure 1. We split kernel elements into many continuous zones, such as U1, U2. Each element in the same zone has the same sign. Inspired by previous example, to maximize out, we should generate perturbations that have the same size as these kernel elements, and we call such perturbations continuous perturbations. In contrast, existing methods generate random noise, which is discrete perturbations, making out smaller. We summarize this point as CNNs are prone to be affected by continuous perturbations. We utilize the CNN weakness to effectively explore CNN defects. However, in black box settings, it's impossible to perfectly match the unknown kernel to generate continuous perturbations. But still, we can approximately match convolution kernels which can still be effective to perform black box testing. In detail, we design two basic perturbation units: square perturbations and linear perturbations. We use these two basic perturbations to match each zone. During the testing, some qualified perturbations will be saved according to our tunable object function, which will dynamically get updated and be approximated to the shape of the underlying convolution kernels. After we have determined how to generate perturbations, we further design an efficiency-centric policy to improve testing efficiency. We first analyze the algorithm utilized by existing blackboard testing methods. We find existing methods tend to generate a batch of test cases in each iteration. Then choose the best one for the next iteration. However, generating multiple candidates brings the query redundancy problem, as all candidates need to query the target model for results. Specifically, as shown in this figure, given n candidates, the best candidate only stems from one of these candidates, while n-1 candidates and their children are abandoned in each iteration. We could imagine the contributing query ratios are 1/n. That's to say, many queries are meaningless, which hugely restricts the testing efficiency. Different with existing methods, we propose an efficiency-centric policy to improve the testing efficiency. In detail, we only generate one test case in each iteration. We further validate our efficiency through modeling the testing process and the stochastic gradient algorithm. The proof process is omitted here. We conduct our experiments on multiple widely used image datasets and models. We use the three commonly used comparison metrics for evaluation. The first one is error number, which reflects the average number of audience inputs per image. The second metric is label length, which reflects the average number of unique misclassified labels per image. The third metric is the success rate, which represents the percentage of original test cases that can find corresponding audience inputs. Then, we show our results. These tables show the results of differential testing on all datasets and models respectively. Overall, our method BAT can acquire more audience inputs with more diversified labels and higher success rate. Such results indicate our method significantly outperforms the state-of-the-art blackboard method. In single model testing series, we still acquire more audience inputs with more diversified labels and higher success rate. We further validate that the audience input generated by us can improve target model's accuracy by nearly 3% with 5 epochs of fine-tuning. We also fine-tune these well-trained target models with only the trained datasets under the same setting, and the accuracy remains the same or even decreases. That's all. Thanks for listening. Any question?